Good morning. Welcome to NGSS Physics. We are going to be talking about Earth's layers today. First off, where did the Earth come from to begin with? Well, scientists believe that the Earth formed about the same exact time that the Sun and the rest of the planets in the solar system were forming, about 4.6 billion years ago. During that time, you had lots and lots of particles coming together due to gravitational compression. This caused elevated temperatures and very, very high pressures. The result of that was, instead of solid particles, what we had were liquidy type particles, molten, meaning melted solid particles, all mixed together. And because those particles in the liquid state can move around a lot better, they were able to then separate themselves and stack as the Earth formed according to density layers. Recall when we talked about density, that's the compactness of the particles. So the more compact the particle is, the higher the mass content per unit volume. Those particles sank to the center of the Earth, while the smaller in density particles floated to the surface of the Earth. Now, the Earth's layering system, there's actually two different systems that we use for Earth's layering system. One's called the compositional layers, and this occurred while that early Earth was forming, while things were still in a molten state. And due to the composition of that molten mass, the high in density substances sunk down to the center, and we call that the core of the Earth. And the least dense substances floated to the top, and we call that the crust of the Earth. And in between, there was an area called the mantle. As the Earth started to cool off, different parts of the core and mantle cooled off at different rates. And because of the temperature and pressure, they're not always in the same state. And so we then have 5 mechanical layers. And those mechanical layers are based on not the composition, but on the strength or the rigidity of the layers as they cooled off and started to form not just molten and liquidy layers, but also solid layers. Not all of the layers are going to be solid. Here are the 5 mechanical layers. We're going to go into each mechanical layer slowly and differentiate them. Notice that the center of the Earth is about 6,371 kilometers from the surface of the Earth. And the Earth in layers, it's kind of like circular layers. If you just think about a spear in the center, and then bigger and bigger spheres, kind of like the layers of an onion. The mechanical layers, we'll start with the very outermost edge of the mechanical layers called the lithosphere. This is the solid most outer part, lithos meaning rocky, and it includes all of the brittle portions of the Earth. Now notice that the lithosphere is not just the crust, it's actually the crust and a little bit of the uppermost mantle. That's what forms the lithosphere. This is the most familiar to us because we live on the lithosphere and the part that we've studied the most. So the rocks that you have in your room, probably all lithospheric rocks. Right underneath the lithosphere is something that is the same in composition as the upper mantle, but because it is a lot warmer and it's a little bit deeper, it's got kind of a plasticky or liquidy nature. Although scientists, hesitate to call it a straight out liquid, they like to call it a plastic. Okay, and here we've got convection currents that can flow very, very freely in this layer. And because of those convection currents, we can get this upper layer, the lithosphere, floating around, kind of like if you're on floating in a pool, and it's not really fixed in space, but the lithosphere kind of floats around on top of the asthenosphere. These are going to be 2 very important layers of the Earth when it comes to thinking about the dynamics of the surface of the Earth and plate tectonics later. Below the asthenosphere, we've got another layer called the mesosphere. And between the mesosphere, the asthenosphere, and a little bit of the lithosphere, that make up the middle mantle area of the Earth. And remember, the mantle is composed of the same sorts of chemicals composition-wise, although they're slightly different when it comes to rigidity. The mesosphere being a solid, the asthenosphere being a plastic-like semi-liquid, and the upper part of the lower part of the lithosphere, which is a little bit of the uppermost mantle, being, of course, rigid like the rest of the lithosphere. And that's where some of the confusion with layers come into play. And the bottommost portion of the Earth, or the centermost portion, is called the core. And at first, we thought the core was all the same substances and the same state of matter. What we found was, although the core is composed of the same substances, iron and nickel, there are two separate parts of the core. One part, which is liquid, and that is the outer core, and another part, which is solid, and that is called the inner core. So those are the 5 mechanical layers of the Earth. You've got the lithosphere, the asthenosphere, the mesosphere, the outer core, and the inner core that make them up. Now, a lot of people would think, well, if we haven't really gotten very far past the lithosphere, how do we know about all of those inner layers? And it comes from doing a little bit of scientific investigation in other fields, like the field of earthquakes. When scientists started studying earthquakes, they found out that earthquake waves, which are called seismic waves, can pass through the solid earth. Although not all earthquake waves will pass through the solid earth and get to the other side. And they wondered why. Well, by looking at 2 of the most popular types of earthquake waves, the S wave and the P wave, they were able to figure that out. S waves and P waves, S stands for secondary and P for primary, are the 2 most popular waves coming out of an earthquake. Primary waves are much faster than S waves, and primary waves can go through both solids and liquids, whereas S waves cannot pass through a liquid. So, for an earthquake scientist on one side of the Earth, where the earthquake occurs, talking to his friend on the other side of the Earth, well, his friend on the other side of the Earth gets all of the P waves, but gets none of the S waves. This tells him something. It tells him that there must be a liquid layer somewhere inside of the Earth that stopped those S waves from getting there. Another thing that waves do is earthquake waves follow wave theory. And waves, when they pass through medium of different sorts, will do 2 things. They reflect and they refract. Refract means that they bend because they have a change in velocity. So when a seismic wave shows some type of change in speed or change in direction, a refraction, scientists know that they must have passed through an area that is a different density. So there are some density boundaries where things are either more or less dense. This tells us that there are different density layers in the Earth. Let me show you another picture. Here is the uppermost part of the Earth, the lithosphere and the asthenosphere. And measuring earthquake waves, scientists discovered that there is a little bit of a dense layer separating the lithosphere from the lower mantle. And it's just a teensy tiny area where the speed of earthquake waves speed up dramatically, which means it's dramatically denser. And they called it the MOHO, okay, right here. And it's because our earthquake waves, when it hits the MOHO, goes from a speed of 6 kilometers per second to 8 kilometers per second. That should be a little slide there. So earthquake waves, evidence for layers inside of the Earth. Other evidence. Yes, scientists are always looking for things to collaborate the evidence that they already have. The other piece of evidence for a layer of liquid inside the Earth is the fact that Earth has a magnetic field. This is really, really interesting because when scientists studied magnetism, they found out that you can actually make a magnet with motion, the motion of metallic atoms. And so having a molten metallic layer made up of iron and nickel in the outer core could possibly be the reason why we have that magnetic field. As that liquid in the outer core moves, it generates electric currents. And those electric currents and the movement of that liquid, they compound upon each other until you get this thing called the Earth's magnetic field. It's not unlike an electromagnet. This magnetic field doesn't exist in planets that don't have a molten core, or the molten core doesn't seem to be moving. But Earth has a gigantic magnetic field, so there must be a lot of metallic element motion inside the Earth somewhere. One cool thing about Earth's magnetic field is it protects us from the solar wind. Charged particles are constantly being emitted by the sun. And if we didn't have this umbrella here of a magnetic field, then those charged particles would hit the Earth, but instead they kind of bounce off and they go in different directions. Right here where the umbrella kind of dips, you might get a little bit of the Earth's, those ions, those solar wind particles hitting the Earth. And that's where we get glowing lights in the night sky like the aurora borealis. Evidence for Earth's magnetism changing and having a molten core means that the magnetic field might not always point in the same direction. And so there was a study of magnetic reversals in Earth rocks. Basically, scientists discovered that if you look at rocks on the ground, they trap in the magnetic pull of the Earth. And it's weird because some rocks are pointed in the opposite direction, which indicates that when they formed, the magnetic field was pointed in a different direction. That's called a magnetic reversal. And by the study of paleomagnetism, paleo meaning ancient magnetism in rocks, scientists determined that the Earth's magnetic field flip-flops. And this is not an uncommon occurrence. It's actually flip-flopped many, many times. And it's perfectly random, but they say approximately 200,000 to 300,000 years, you could expect a flip-flop. Okay, it's not uncommon at all, and it's happened several times if you look at the magnetic rocks that are on the bottom of the ocean, which we will do when we think about plate tectonics. Okay, let's pause and do a few sample questions here. Which layers are liquid or plastic? Okay, if you said this layer here, number 6, which is also be 3A, then you would be right. That's the liquid outer core. The other layer that is a little bit fluidy is this layer here, number 5. That would be the plastic layer called the asthenosphere. Okay, number 2. Which layers make up the lithosphere? Well, it's not just the crust, which is this top layer, it's also a little bit of that mantle, the toppermost layer. So both of those, I would say number 4. Number 3, which ones create the Earth's magnetic field? Well, this is the core. The core creates the Earth's magnetic field because that is where we're going to get those metallic elements, and not just the core, but this layer right here, the outer core, in which those elements can fluidly flow around. Number 4, which evidence supports the theory of a liquid outer core? Well, we've got 2 things that support this theory. Number 1, earthquake seismic waves. S waves can't get through a liquid. And so there must be something about liquid blocking them. And it's about the size of the outer core, believe it or not. Number 2, Earth has a magnetic field. And we can't have a magnetic field unless we get some motion of magnetic elements, which the outer core is actually made up of. So those 2 things. Temperature and pressure. Okay, it makes sense that the temperature and the pressure will increase the deeper you go into the Earth because you've got things stacked on top of each other. You've got heat being, trapped within the Earth by the outermost layers. So both temperature and pressure increase with depth. Here's a little scale of temperature versus depth. You can see as you go deeper, the temperature rises dramatically in the lithosphere. And then it doesn't rise as much through the lower mantle, but then it gets very hot once you get to the inner core. Here is a little graph of pressure versus depth, and you can see that the pressure jumps up, and as you get deeper and deeper, it goes up dramatically. So pressure and temperature both increase the deeper you go into the Earth. We talked a little bit about heat, and when the Earth first formed, it was very hot. And from that time, heat has slowly been escaping the Earth, and the Earth has been cooling off. But right now, we're kind of in a state in which the heat that's being given off and the heat that's being produced inside of the Earth are about equal. And so we're not really cooling down very fast like we were at the very beginning of Earth's formation. Where is this inner heat coming from? Okay, inner heat inside of the Earth is actually coming from a reaction called radioactive decay. And here's a little example of what radioactive decay looks like. A parent isotope, which is an unstable nucleus, will break into pieces. And when it breaks into pieces, we call that radioactive decay, in which a small piece gets broken off and a bigger piece gets left behind. When that small piece gets broken off, a little bit of energy is also given off. And that energy we feel as heat, and it warms up the earth. So the earth makes its own heat through a process called radioactive decay. And this is still going on today. So there's still a little bit of heat being generated in the deep recesses of the earth. The other heat the earth gets is from the sun, but that heats the outside, not the inside of the earth. So right now we're kind of in a state of the heat that's being produced and the heat that's giving off is about equal. And so we're not really cooling down very much. It's very, very slow. Let's talk a little bit about radioactive decay. Radioactive decay doesn't occur with every element. You have to have a radioactive element, which is an unstable nucleus. And when that unstable nucleus breaks down into pieces, it actually forms a stable nucleus, one that no longer decays. So it goes from radioactive uranium, for instance, to stable lead, a whole different element. And when it does that, a little bit of energy is given off in the form of heat. So all of your uranium-235, okay, can decay into lead-207, and then you no longer have this. When that happens, there will no longer be heat being generated inside of the earth. But this is a very slow process, and it takes a long time. What I have here is a graph that shows the half-life of uranium-235. If the green line represents radioactive uranium, and the gray line represents the stable lead, we can see that both of these lines are kind of a reflection of each other. As the uranium is slowly decaying and disappearing, the lead is slowly being created and appearing. And so they should be a direct reflection. Let's take a look at some sample questions I might ask you about the radioactive decay of any substance. What is the age of the sample of lead ore if there is 61% lead and 39% uranium? So these two percentages always have to add up to 100, okay, for this to make any sense at all. So let's take a look. Here it is, 61% lead and 39% uranium. They hit the graph in the same exact spot because one of them decays into another. And you can see that the age is 1,000 million years. Okay, not just 1,000 years, but 1,000 million years. 50% uranium and 50% lead. So here's the 50% mark, and you can see that that's where they cross right there. You go straight down and you say, oh, it's less than 1,000 million years. Maybe it's 700 million years. How about if you got 5 kilogram sample of the ore, and 4 kilograms is lead, 1 kilogram is uranium? Well, this is actually, we can't do this without figuring out what percent is lead and what percent is uranium. And if you recall, a percent is a very simple problem in which you take the part, divide it by the whole, times 100. So if we want to see which part is lead, okay, I would say, okay, 4 kilograms is lead, okay? That's the part that's lead. The whole is 5 kilograms is the whole, and I times that by 100, and what do I get? 80%. So 80% is lead, which means 20% has to be uranium, because those percentages, they have to add up. And you'll see that they are going to fall at the same spot in the graph. There's 80% lead, here is 20% uranium, and you can see they fall right about there, which is somewhere around 1,800 million of years. All right, in summary, Earth's layers are density layers, and they formed when the Earth was a molten mass. Seismic waves provide evidence for the different layers. They speed up as the density changes, change direction as the density changes. Some seismic waves can't go through a liquid, like this liquid layer here, and so therefore they completely stop. That would be the S wave. Earth's magnetic field provides further proof that you have that liquid outer core because that molten metal is in motion, causing the magnetic field. The heat of the inner Earth comes from heat left over from Earth's formation and from radioactive decay. Thanks for listening. I'll catch up with you a little bit later.